All right. Hello, everyone. Welcome back to the second lecture in the mini course on two Siegel spaces in homotopy theory, algebra, and algebraic K-theory. And from here, we'll have Julie Bergner.
Great. Thanks again, Sarah, for the introduction. So last time I introduced just the discrete version. So I talked about, one Siegel and two Siegel sets. So these are just simplicial sets satisfying some properties. And so today we have two goals. One of them is wrapping up something I thought I might get to last time, but didn't. And that's talking about two Siegel spaces. And more generally, although I won't say too much about them right now, are just more general two Siegel objects. And then I want to, sorry, was there coming? And then how they arise from Waldhausen's S dot construction, which is important for algebraic K-theory. Okay, so for our first goal, so last time we talked about simplicial sets, we're going to be interested here in simplicial spaces, which I'm going to use, well, typically when I say this, I really mean functors from this category delta op into simplicial sets. But because I'm really thinking of simplicial sets as models for spaces, if you want to think about this as functors into top, that's generally going to be okay too, if you literally want simplicial spaces. So then we can talk about one Siegel spaces, and just called Siegel spaces. And so now these Siegel maps that we talked about last time, they go from Xn to this iterated pullback of copies of X1 along X0. So we had N copies. Well, now these are going to be spaces or simplicial sets. So I'm gonna make this a homotopy limit on the right-hand side. So everything is homotopy invariant. And now we want these maps to be weak equivalences for every N at least two. And then we talked last time about how one Siegel sets, where these maps are just isomorphisms of sets, are just categories, essentially. They're nerves of categories. And so what we get here are, well, again, simplicial or topological, depending on your preference, category, and then up to homotopy, because we're not asking that these maps be isomorphisms or homeomorphisms. We're just asking if they be weak equivalents. So everything's kind of up to homotopy. And notice, because it's a little ambiguous sometimes what you mean by a simplicial category, these are things that have both spaces of objects and morphisms. So X0 is like a space of objects and X1 is like a space of morphisms. Okay, so then we can just do the same thing to get two Siegel spaces. So we have these two Siegel maps that now go to a bunch of copies of X2 along X1. There'll be N minus 1 copies. And again, we'll make this a homotopy limit. And these maps are all weak equivalences. And recall that we get one of these maps for every N at least 3. And there's multiple of them. They also correspond to triangulation of a cyclically labeled triangulation of a regular N. And just a reminder, and just if anybody wasn't here, and because I'm going to refer to this map again. So one of these maps arose from where we take this diagonal here and we include it into a 3 simplex. And so this would be a map from, this would induce a map from x3 to 2 copies of x2 over x1, and this would be the map given by d0, d2, since those are the faces of a 3 simplex that give you these two, that would give you this configuration. Okay, and then in this case, if since two Siegel sets model something weaker than a category where you have this sort of partially or multi-valued category, well, again, we would get some kind of simplicial or topological multi-valued category to talk to. So the same kind of thing where composition may not exist or be unique, but is associative. Okay, and then there wasn't anything particular really about simplicial sets or spaces here. So we can generalize two simplicial objects in a sufficiently nice category. Basically what you need, well, in order for these maps to make sense, you need to sort of have enough limits, and you need some kind of weak equivalence. So, you know, for example, you could do this in a model category, or you could do it in some more general, say, infinity one category, say with limits. And let me really briefly, just for people who are interested, and I'm not going to spend a lot of time on, it's not going to be a focus, but let me say a little bit about model structures here. So the underlying category here is just the category of simplicial spaces. And then there's the injective, which is the same as the reedy, if you know what that is, model structure. And this is where you take just level-wise weak equivalences and cofibrations of spaces. And then we can get model structures for 1 and 2 Siegel spaces via left Bausfield localization.
So sorry, are we to assume in general that 1 and 2 Siegel spaces are really fibrant then?
Yeah, so that's a good question. It depends a little bit on the setting. I tend to assume that they are in practice, but it depends on which reference you're reading and what they want to assume. So
Okay.
I mean, one nice feature if you do is then like you can just take regular pullbacks here rather than homotopy pullbacks and things like that. But that subtlety is not really going to come up in what, certainly not in what I'm going to today, and probably not in what follows either.
Okay, are they like also not projective fibrant even? They could just be simplicial sets.
Again, in some references, people want to actually start with the projective. I mean, you could do projective here, and then localize that. It just depends on the setting, but it's not, again, not going to be so important here. Yeah.
Okay, great, thanks.
And so the idea is if you want 1 Siegel spaces, then you localize with respect to these maps, Gn to delta n. So these were these things that just like look like strings of composable arrows, including as the spine. And if you do that, you get something where the fibrant objects are one Siegel. And yeah, if we're localizing the Reedy model structure, they'd also be Reedy fibrant. And then we have these sort of inclusions of these triangulations of polygons into delta n for every n greater than or equal to 3, and triangulation of an n-gon, and then you'd get something where the fibrant objects are 2C. Okay. All right, and that's basically all I'm gonna say about that. It's mostly just for people who want to, when I'm gonna refer to them later, you have, something to make you feel more secure about it. If you're not familiar with model structures at all, then don't really worry about it. Just think about it as a setting in which you have some notion of weak equivalence. Okay, so now I want to switch gears and talk about the S-dot construction and a little bit of motivation for it. So one of the classical inputs for algebraic K-theory. So I'm gonna guess the most classical input is a ring, but I'm gonna skip ahead in history a little bit more. And that's that of an exact category. And if I'm not gonna go through the formal definition of them, you should think of this as something in which short exact sequences make sense. So it's something, they're more general than abelian categories, but and momentarily I'm gonna spell out actually what part of this I care about. And so if I have an exact category C, we can define, so it's Grothendieck group K0 of C. And this is just the group generated by isomorphism classes of objects. And then we mod out by the relation, where we say that C is the sum of B and D, again, working on isomorphism classes, whenever I have a short exact sequence, B to C to D. All right, so that's a starting point. Now to define, so higher than 0, algebraic K groups. So one approach, and this is fast forwarding even a little bit further in history to Waldhausen. Well, this is going to use the following features of an exact category. And well, you can actually say, well, forget about it needing to be exact. You just take the features I'm about to describe. And this is what's sometimes called a proto-exact category. An exact category will have some more structure, but it's not gonna matter. This is what I really care about. Okay, so the first thing I want is that this be a pointed category, which just means that it has a 0 object that I will denote by a star. Okay, the second thing is that, well, I mean, we're talking about short exact sequences, and when you have short exact sequences, you have things that sort of appear in the first, well, other than the spot involving 0, the first spot. We think of these as admissible monomorphisms, things that appear in this spot in an exact sequence, and then we have admissible epimorphism. Now, if you're in something like an abelian, categories literally are monomorphisms and epimorphisms, but the upshot is we have two distinguished classes. So we have classes M of admissible monomorphisms which we'll write with this little hooked arrow. And this is going to contain the unique map from I'm sorry, I shouldn't write that as 0. I should write it as a star. From the 0 object to A for all objects A. And script E of admissible epimorphisms. Which I'll write as I did above with this little two-headed arrow. And this is going to contain the unique map from A to the 0 object for all objects A. And both of these classes are going to be closed under composition. And containing all isomorphisms. Any isomorphism is both in both classes. Okay, and then so the third thing we're going to use is that a commutative square in our category. So say this one here. So I want my horizontal maps to be admissible monos and my vertical maps to be admissible epis. And this is going to be Cartesian if and only if it is co-Cartesian. So it's a pullback square if and only if it's a push-out square. These agree, and so we call this bicartesian. And then finally, these squares will be determined by either this span or this cospan. So if we have any configuration of an admissible mono, is admissible epi, and any, well, the other way around, cospan can be completed to a bicartesian square as above.
Julie, one of those B's should be a C, correct?
Oh, yes, thank you, yeah. Thank you, yeah. That should be a C. Yes, it's all supposed to, they're all supposed to sit in the same place. And this is basically by taking a push out or a pullback, and this is in some like essentially unique way. Unique up to isomorphism or something. Not strictly unique, but the usual thing you would expect for push outs and pullbacks. Okay, so the canonical example of this is if you take R modules, really in abelian category, with the usual monomorphisms and epimorphisms. But just to give an example on the other extreme where we actually don't even require exactness, but we sort of something that satisfies all of this, but doesn't have sort of the algebraic structure that you might think of, is the category of pointed sets. Maybe I'll just say finite just to be safe. And you can take M to be just the injections. And then E, you can take, well, you might say surjections. We need a little qualifier here. You can take surjections with, well, basically you just want the pre-image of everything that's not the base point to be a single point. And so that's something, so you can check that all these things make sense here, if these last two conditions hold in this setting. So this is a very non-algebraic kind of example. Okay, so now assuming that we have these, so let me define Waldhausen's S dot construction. Again, I'm just going to assume this sort of proto-exact business. Basically, just assume the things that I've just described. All right, so this is going to be a simplicial object in groupoids. So I'm going to take S0 of C. This is going to be the groupoid of 0 objects of C. So, I mean, if this is a groupoid, if you take its, geometric realizations, it's just going to be some contractible space because your 0 object may not be unique, but it's unique up to unique up to unique isomorphism. So S1 of C is going to be the groupoid. Well, I'm going to say this in what's going to seem like a silly way, but you'll see that's part of a pattern. So this is going to be a groupoid of diagrams of the form. Well, basically, it's just going to be objects, say A of our category, but I'm going to think of it as a diagram where I equip A with its unique map from the 0 object and its unique map to the 0 object. So essentially, it's just the groupoid of objects. So isomorphism classes of objects. Okay. Again, that seems like a weird way to talk about the objects, but now let's go up a level. Now we're going to take the groupoid of diagrams. And so now I have a little bit longer row, and so I'm going to label these. I'm putting in these zeros. You should think of this as like A00 with this indexing. This would be, well, this would be A11, but it's the 0 object. So we have a little diagram like this. And again, we want to make sure this square is bicartesian. Following our structure. And if you think about this, if you are in an exact category where you talk about short exact sequences, that's exactly what this is. So the interesting structure here, not involving the 0 object, are that you have an admissible monomorphism here, and then you have an admissible epimorphism here. So this is encoding short exact sequences or something sufficiently like it. And now the very general case, so SNC is going to be the groupoid of diagrams. So we just extend this pattern. And so we just have something of length N here. And we end up with these 0 objects along the diagonal. And then eventually we just get a 0 object down here. And again, we want all the squares to be bicartesian. All right, now I claim that these assemble into a simplicial groupoid, simplicial object in groupoids. Now the simplicial structure, so if we need to know what the face and degeneracy maps are. So the face maps, DI, are going to remove, just say this rather loosely, remove everything with index I.
It looks like there's perhaps a question.
Oh, yeah, go ahead.
Yeah, I'm sorry. When you were writing S2,
Uh-huh.
where does A 02 come from?
You're just basically you're just saying look in your category C, and whenever you have a diagram that looks like this, whenever it exists in your category with this square being bicartesian, then you include it in your groupoid. So it's just you're observing where this diagram occurs in your category.
Okay, so it may or may not. Just
Sure.
if I
Yeah.
find it. Okay, cool.
Right. I mean, you're
Thank you.
always gonna have, like, you could just fill these all in with the zero object, so it will never be empty, but.
Yeah.
But yeah.
Okay.
So You're
Okay,
just
thank
saying, take every time I see this configuration, take the groupoid of all of those. Yeah.
Okay.
Yep. Okay, so let's just look at a two simplex. So a general two simplex, so remember that looked like this. And so we expect three face maps. So the outer ones are the easiest to do. So if I take D0, that just means sort of chop off the top row here. And so I'm just left with this one simplex here. And D2 is similar. I just leave off this whole column. Okay, and then so the trickier one is D1, and that's where I say remove everything with index I. This is where it's helpful to remember that this is A11, and you say, okay, I'm just gonna cut out this whole little piece here and then take composites as necessary. And so I'm just gonna be left with this composite map from the zero object to A02, and then this composite back down to the zero object. So that's how the face maps work. And then the degeneracy maps. SI, they just repeat entries with identity maps. So as an example, let's just take a one simplex, something like this, and then say, well, what happens? So if we apply S0, then we're just going to, well, we're going to put this sort of downstairs, and then we'll just sort of copy everything to obtain another row here. So we get an A01, and then we just get the zero object, and we get another zero object. And then S1 would do the other possibility where you put this up here. And then just copy everything over to get this extra column here. So that's the simplicial structure. All right, so now if we take, so let me just make a comment now about the connection with K-theory here. So if we take the level-wise nerve, so this is going to give a simplicial space. And just by abuse of notation, because this is mainly what I'm usually going to work with, I'm also just gonna write this as S dot C. And it's, now this has a realization, which is a simplicial set. In that case, it's just the diagonal, or there's a realization to get a space. And that's what I'm gonna denote by with the bars. That's why I didn't want to use the bar for this thing, because I'm gonna use it for this. So this is a space. Okay, and then something that you can try to check here, beyond the scope of what I want to do here, but if you take the fundamental group of this space, then this ends up just being this K0 of C that I described before, if you have, say, an exact category. And so we can then define the K-theory space of C to be, we'll call this K of C. And well, we don't want this sort of discrepancy where this is a 1 and this is a 0. So we just bring everything down by taking the loops. So we just take the loop space of this realization of S dot C, and then we take the K groups. So Ki of C are defined to be just the homotopy groups of this space. And then if you want to, these will just end up being shifted up by 1, the homotopy groups of this realization. So this is a bit more here just for motivation, like why people care about this S dot construction. I mean, why it was defined in the first place. Okay, so now a theorem, and this was proved independently, both by both groups of founders of two Siegel things. So this is Dickerhoff and Kapranoff, but then this was also proved by Galvez, Curio, Koch, and Tonks. And that is that, well, before we take this realization, if we just take S dot C, and again, you can think of this as a simplicial groupoid. I'm going to implicitly take the nerve and think of it as a simplicial space. This is a 2 Siegel space. So let me give you an idea. Let's just look at one of the 2 Siegel maps. This is why I reminded you of one of them at the beginning of the talk. So let's check why this would be. So let's look at this D0, D2, and we're going to think of this map from S3 of C to S2. That's S2 over S. All right, so a 3 simplex, according to our definition, looks something like this. Okay, now following our definition of face maps, so D0, I'm gonna write this in green. Again, that's just gonna chop off this top row here. So I'm gonna be left with this green diagram here. Okay, now D2, if we're applying D2 to a 3 simplex, so that's going to cut out this L-shaped region. So it's everything that has a 2 in it. It's going to get cut, and then we'll put in composites as necessary. So that is going to look like this diagram. So, all right, this map is always going to exist. So you can see that we have the green 2 simplex and the pink 2 simplex. And then you have this one simplex that's sort of overlay of pink and green. Now, if this is to be a 2 Siegel space, then we need to be able to complete this diagram essentially uniquely. And we can do that because, well, we can look at this little cospan here, and we can just say, all right, well, let's take A02 to be the pullback of that square. And then, well, we'll get the map that we need here by the universal property. And so, because pullbacks are essentially unique, that tells us that we can't really get, you know, in the setting of the original groupoid, you know, up to isomorphism, right? We're defining this. And so we're getting something that's 2 Siegel. Of course, you've got to check that this works for, you know, everything, not just this one map, but that's the idea. Now, this is also interesting because it's not 1 Siegel in general. So if we wanted to check the 1 Siegel condition, so we were looking at, say, let's just look at S2 to S1, cross S1, S0. So what you're looking at here, you have 2 1 simplices that agree along a 0 simplex. That looks like a diagram like this. And so in order for this map to be a weak equivalence, you would have to be able to fill this in and uniquely. And that it's not always possible in the most general setting. And well, if you're in something like an abelian category, then you can say, like, take the direct sum of these, and you can always put it in, you always have the split exact sequence, but you can say, well, this is coming down to not all extensions split. If you're in the actual algebraic world where we're really talking about short exact sequences. That this is not unique in general. In general, there are more extensions. All right, so then just a side comment. I mean, if you're familiar with Waldhausen's construction of this, Waldhausen actually made this construction for something more general than what I'm talking about here. He defined it for, well, Waldhausen categories, or you could just say categories with cofibrations. And or you could take Waldhausen categories where you also have weak equivalences, but this is what it would make sense more or less from what we've done. But you only have one distinguished kind of morphism, cofibrate. He calls them cofibrations. We would call them, admissible monomorphisms. And then you have some kind of push out requirement. But you don't. So for example, if all you had was that, so you sort of said, all right, require, your horizontal maps to be cofibrations, and then somehow you get your squares by pushouts, you would be in trouble if you were trying to check this condition in general, because you don't have pullbacks. So you can't this map would not necessarily be a weak equivalence anymore. So couldn't necessarily complete this above diagram.
Is there
Um,
a weaker version of a two seagull
there-
space that this would be?
there is, yes. I was just, so you get, well, I could say half.
Sorry.
It's in some sense, not, it's not really. Get half the structure, and this is something called lower two seagull. And so I'm just gonna refer you, this was actually investigated by my student, Tanner Carawan. And the paper about this should be appearing on the archive any day. He, in his paper, I should say, he calls it left two seagull. But it ends up being, and he verifies this in his paper, that it matches this other notion in the literature called lower two seagull. So the idea is you somehow, you get the two seagull conditions that you can sort of fill things in using push-outs, but without pullbacks. So
It looks like we have one more question.
yes, and thanks
Um,
for alerting me. I don't always notice. So yeah, go ahead.
Is this when you say it matches a notion? Do you mean Walday's notion? Lower seagull, lower two seagull?
It didn't originate with Wald. It's what's in Walda's paper. It did not originate. I believe it's originally due to Dickerhoff and Paguntka, but Walda also uses this.
Oh, okay, yeah. That's what I meant. My bad. Yeah.
Yeah. Yes. But it's that notion.
Okay, great.
Mhm. Okay. All right. So now, let me ask another question, because I mean, I've kind of been saying, well, you can generalize this in one way and not, we could substantially generalize from being abelian or exact, but we can't quite generalize to Waldhausen categories with cofibration. So what is the most general input for S dot for which the output is in fact two seagull? All right, so let's look again at this input data and see if we can generalize it a bit more. And so for simplicity, just so I'm not sort of throwing simplicity, too much simplicial. I'm going to take a S dot that is discrete. So we're going to take sets of diagrams of the above. And then S dot C is a simplicial set. So everything is very strict now. This is just so that there aren't really particularly useful examples here, but I just don't want to kill you with too much abstraction in what follows. So hold with me here. So the first thing that we needed, I mean, we had these admissible monomorphisms, admissible epimorphisms. So we need some kind of things that are horizontal in our diagram. And we need things that are vertical in our diagram. That assemble into squares. And again, I'm going to use these notations. So they assemble into squares where the horizontal morphisms are horizontal and the vertical morphisms are vertical. And this is something that you can do. This is what's called a double category. So the idea here is that you have two different categories. They have the same objects. So the objects of each category are the same, but you have a category consisting of objects and horizontal morphisms. You have an object considered, sorry, you have a category consisting of objects and vertical morphisms. But then you have this further structure. So in fact, you have more categories. You have the category whose objects are vertical morphisms and whose morphisms are squares, and you have a dual version. This is also what's called a category internal to categories, if you've heard of that. But the upshot here and why this is a generalization is we no longer require that both kinds of morphisms live in an ambient common category, which we did before. We don't need them both to be morphisms in a common ambient category. All right, but then that presents some new difficulties, because if you're not in a common ambient category, then it doesn't make sense to talk about bicartesian squares. You can't take pushouts and pullbacks unless everything lives in a category altogether. So since bicartesian squares no longer make sense, so we basically ask for the same kind of thing to hold, and we call this stability. So this says that anytime I have a span of a horizontal and a vertical, or a cospan, this other configuration, then this is going to, in this case, in this discrete case, completely uniquely determines a square. So that's our replacement for this bicartesianness. And then the last thing that we need is the analog of a zero object. And this is what's called a pointed double category. And if you look at where this is going to sit in these S dot diagrams, then you say, well, we have a unique object star, and it doesn't have to be a zero object in both categories. It just needs to be initial in the horizontal category, because we're always just looking at, things like this. But then it has to be terminal in the vertical category. Because in our diagrams, we, again, always just have something. So we want those maps always to exist and to be unique. Now notice, if I do this for this sort of discrete S dot, that means that S0 is always just going to be a single point. And so if we have this assumption, we will only get reduced to Siegel sets. So that means that K0 is literally a point. If we want to get more general ones, things with more interesting sets of zero simplices, we can take something called an augmentation. And this is a very odd sort of condition. So this is a subset A of the objects such that for any object X, we have a unique map, a unique horizontal map A to X, and a unique vertical map from X to B with A and B in the augmentation. So they don't have to be the same, and they're not, in particular, they're not the same. For any object X, you have an A and a B, but if I give you a different object, they might have something different.
Sorry, are the objects unique as well? Not just morphisms.
Yes, so given, you're right, so given any object X, there is a unique A and a unique map A.
Right.
Yeah. Exactly.
Okay, fine, thanks.
Everything you could possibly ask to be unique is unique. Okay, so in this sort of discrete setting, so this is a theorem this is joint work with Angelica Esorno, Victoria Zornova, Martina Rovelli, and Claudia Scheinbauer. And that is the discrete S dot construction defines an equivalence of categories. Between augmented stable double categories and two Siegel sets. So if it's an equivalence, then, well, there's an inverse equivalence. So let me say a little bit about what that does. So the inverse functor P takes a two Siegel set K to the, so this is a double category P of K. So I need to tell you, well, it's going to be a double category with augmentation. So the object set is going to be K1, the set of one simplices. You might say, well, what happened to the zero simplices? Well, they're going to be the augmentation set. And again, that if you think of what's happening on the S dot, right, your S0 is just going to be the collection of things that appear in the augmentation. So this is, and you know, where your objects appear in your double category, they end up being corresponding to one morphisms when you take S dot. And now things get a little bit weirder here. So you want to know what the horizontal morphisms are, and you want to know what the vertical morphisms are. And they are both going to be given by the set of two simplices. But as we'll see, the structure is different. And I'll give you an example in a moment. And then the squares are going to be given by the three simplices. So let me, to finish off today, just tell you how this works for this example of a partial monoid. This is one of the examples we talked about last time.
I'm sorry.
Yeah.
When you say that the horizontal and verticals are both K2, do you mean
Yeah.
that each of them is a copy of K2 or they split?
So this is going to be a small double category, so it has a set of horizontal morphisms and it has a set of vertical morphisms. Each of those as a set will be isomorphic to the set K2. But then when I say the structure different, the way you get like source and targets down to the objects and such, they're not going to be the same. So they're not going to be equivalent categories in general. But they will just, if you just sort of forget all the structure and just look at the collection of morphisms, they're going to be isomorphic and given by K2.
Okay.
Yeah, it's a little odd, but that's what it is. Okay, so in a partial monoid, we have composable pairs. So this is a set with an operation, but not necessarily everything multiplies with everything else. So we had this subset M2 of M cross M. And so if I take an element, say AB of M2, so that's a two, so this is, right, this was a two simplex, when we think of it as a two Siegel set, of the corresponding two Siegels. And so how that's going to look as a vertical morphism. So I'm going to think of that. I have the element A dot B. This is a composable pair. So A dot B is defined. And this is going to define a vertical morphism from A dot B to B. Maybe I'll call it A dot since it's sort of, left multiplication by A. But as a horizontal morphism, it's going to correspond instead to a morphism from A to A times B. So maybe we write this as dot B. It's right multiplication by B. So these look very different with the sources and targets of them and, how they're going to interact, with each other. It's going to be quite different. And then let me say a word about the squares. So these should be, so if I have a three simplex, so A, B, C, this is in M3. So this should correspond to a square. This is going to look like, well, I'm kind of assembling as I can here. So I get sort of A dot B down to B. This is this little A dot. And then, well, I can think of this two ways. I have like a dot C. This would correspond to sort of this bracketing A dot B dot C. Here I have a dot C, which would go to B dot C. And then, well, if I have this associativity, this should be the same as A dot B dot C, and then this should be sort of this vertical morphism, A dot. And you sort of, associativity is also how you can see the stability. Because they're saying, all right, if I have this span, that should uniquely determine something and a square, and similarly this cospan can. Well, and the key is this equality, that these two bracketings are the same. And so, well, then this thing had to come from here and so forth. So if you want, since I'm out of time, if you'd like to play around with what this might look like for that other example of the cobordisms with genus constraints, I invite you to do that. And then I'll next time I'll start off with sort of the space version, the up to homotopy version, which really encodes, sort of real examples like those coming from exact categories where things aren't so strict, and I'll say more about that, and then I'll move on, I think, to Hall algebra stuff after that. So that'll be next Tuesday. So I will stop there.
All right, let's thank Julie for the lecture.